Hi folks, welcome to the second part of this lecture. In this second part, we are going to look at heat energy and temperature, we are going to look at calorimetry, and we are also going to look at heat energy and chemical reactions. So let's start with heat energy and temperature. So when we talk of heat, at times we often confuse the difference between heat and temperature. So let's make it clear here. When we talk of heat, we are talking of the total kinetic energy that is transferred from one substance or object to another. So with heat, there is transfer of energy. Now, with temperature, temperature is simply the average kinetic energy of the particles in a substance. So heat involves the transfer of kinetic energy, while temperature simply is the average kinetic energy of the particles within a substance. So here, when you are seeing this pot, as you see the pot here, when you are calculating the heat, when we talk of the heat, is the energy that is transferred from the system to the surrounding. And when you talk of the temperature, you simply just measure the temperature of the system. Now, we are going to look at what is called specific heat and heat capacity. So the specific heat can be defined as the amount of heat that is required to change 1 gram of a substance by 1 degree Celsius or 1 degree Kelvin. Now, let's look at this situation here. If we have 1 kilogram of water and we apply 100 calories of heat to 1 kilogram of water, the temperature is going to increase by 1 degree Celsius. Now, if we use a kilogram of iron and apply the same amount of heat, which is 100 calories, we see that the temperature is going to rise by 9.3 degrees Celsius. Why is there a difference in the way the temperature rises? This is because of the substances that make up the material, the water and the iron. Now, let's look at specific heat. I've said specific heat is the amount of heat that is required to raise the temperature of 1 gram of material by 1 degree Celsius. Very important here, 1 gram and 1 degree Celsius. Specific heat. At times, it is called specific heat capacity. So if you see specific heat or specific heat capacity, it is the same thing. Now, the specific heat is expressed by the formula, the heat divided by the mass times the change in temperature. So, mathematically, specific heat is we denote it by S, and heat is denoted by Q. Mass here is denoted by M, and change in temperature is denoted by delta T. So, to simplify this equation so that you can always remember it, it is given by Q is equal to ms delta T, where Q is the heat, M is the mass, S is the specific heat, and delta T is the change in temperature. So remember this formula. You will need it anytime we are talking about heat and specific heat. Talk about use this formula all the times. So different materials have different specific heats. As we are going to see in this table here, we have so many different materials and their specific heats vary. I want you to take a very good look at the specific heat of water. In this case, we see here that the specific heat of water is higher than all of this other material. What does that mean? This means that it will require a very high amount of heat to raise the water by 1 gram. So this helps in the way that it is difficult for our temperatures to easily vary. Now, an example of this situation, we are going to look at the specific heat of water and the specific heat of sun here, for example. If you are by the beach on a hot sunny day, what you realize is that when you walk on the sun, it is super hot, but when you touch the water is still cold. That is because the specific heat of water is very high, so you need a very high amount of heat to raise the temperature of water. But that same heat is going to raise the temperature of sun so easily. So that is very important to note. Now let's look at an example where we are going to apply a formula to calculate some parameters here. How many kilojoules of heat are required to raise the temperature of 120.0 grams of water by 5.0 degrees Celsius? So we are calculating heat here, and from the formula we've seen, we need to always take that formula. Q is equal to ms delta T, where Q is the heat, M is the mass, S is the specific heat, and delta T is the change in temperature. Now let's collect our data here. The mass has been given to be 120 grams. The specific heat of water, as we just saw from the table, is 4.184 joules per gram per degree Celsius. And the change in temperature is by 5 degrees Celsius. So when you see by 5 degrees Celsius, it means that the change is 5 degrees. If you were told that the temperature changes from a particular number to another number, you are going to use the difference in those temperatures, as you will see in the second example here. So what we are going to do here, we are going to cancel out the unit to have our unit of joule. So you see here we are left with joule, and if you multiply that out, you are going to have 2,500 joules. The question asks us to calculate how many kilojoules. Now, how do you convert from joules to kilojoules? I presume you still remember what we did in the earlier chapters. So you are going to divide by 1,000, so that gives you 2.5 kilojoules of heat that are required to raise the temperature of 120.0 grams of water by 5 degrees Celsius. Now, let's see how we can compare specific heat and heat capacity. We've said that the specific heat, which is abbreviated by S, is the amount of heat that is required to raise the temperature of 1 gram of a substance by 1 degree Celsius. And we've stated that to determine the specific heat, we have to use the formula Q is equal to ms delta T, where we will make S the subject of the formula, like we see here, and S is equal to Q over M delta T. So when we know exactly the material we are talking about, for example here this block of iron, we can determine the specific heat. Now, in a situation where we are dealing with a heavy container, for example, engineers or scientists are working in the chemical industry and they have a big container that contains some substances, we are unable to measure the specific heat because we will have to measure the specific heat of each of those substances contained in that big container. So what we make use of in that situation, we use what is called the heat capacity. So the heat capacity, capital C, is the amount of heat required to raise an object by 1 degree Celsius. So here for the heat capacity, you don't see the 1 gram. So it is just the amount of heat that is required to raise an object by 1 degree Celsius. Now, to calculate the heat capacity, which is capital C, we are going to divide the heat by delta T. So for us to easily memorize this formula, we are going to do the same like we did for the specific heat, where we say Q is equal to ms delta T. So for the heat capacity, it's going to be Q is equal to C delta T. So the heat for the specific capacity is ms delta T. So when you're talking about the heat capacity, the Q is equal to C delta T. So here we have a big container that has so many different things inside, and we can only easily measure the heat capacity and not the specific heat capacity. So let's look at the second example here. When filled with water, a large reaction vessel in the chemical plant has a heat capacity of 5.41 times 10 to the 5 kilojoules per degree Celsius. How many kilojoules of heat are required to heat this entire vessel from 25.0 degrees Celsius to 48.2 degrees Celsius? So we are talking about the heat capacity here. So the equation that we are going to use is Q is equal to C delta T. Okay, now the next thing is we are going to calculate the change in temperature, because we have, like I told you in the first example, it was changed by. Now I just said in the second example, which is what we are looking at, we are going to see that the temperature is changing from one value to the other. So to calculate delta T, we are going to take the final temperature, which is 48.2, minus the initial temperature, which is 25.0 degrees Celsius. So that gives you a value of 23.2 degrees Celsius. And to calculate the heat, we are going to substitute the values of C here. We've been given C to be 5.41 times 10 to the 5 kilojoules per degree Celsius. So we are going to multiply that by the change in temperature. Now that gives us 5.41 times 10 to the 5 kilojoules per degree Celsius times 23.2 degrees Celsius. What will cancel out? Degree Celsius cancels out and we are left with kilojoules. So if you carry out that calculation, you will have a value of 1.26 times 10 to the 7 kilojoules. Now we are going to look at the next thing here, which is calorimetry. So what is calorimetry all about? So when scientists or chemists are dealing with experiments where there is the flow of heat from one substance to another, we use what is called calorimetry to measure those changes in heat from one substance to the other. And in this lecture, we are going to see two of the calorimetric methods that are used. The first one is the coffee cup calorimetry, just like the way it is coffee cup. It uses a coffee cup, and the second is going to be a bomb calorimetry. And for bomb calorimetry, it is not a bomb, please. So let's see what the coffee cup calorimetry is all about. With the coffee cup calorimetry, it involves a cup here, a coffee cup which is insulated, is really insulated, and it doesn't allow the exchange of heat between the system and the surrounding. So the heat that is found in this system will not be given out to the surrounding. So for the coffee cup, everything that happens in the system here inside the cup contains a lid, and there is an opening where we can put in our thermometer and measure the changes in temperature. Then we can introduce whatever substance we want to work with in this system. So for this particular case, we are going to be using a block of iron, and what happens is that there is water inside the calorimeter, the coffee cup calorimeter, and we are inserting the block of iron into the water. So what happens is that the amount of heat that will be lost by the iron will be the same amount of heat that will be absorbed by water. Remember, we talked of the law of conservation of energy. So energy cannot be lost here. So we are going to state a formula for this. So all the heat from the metal is absorbed by the water. Now, since we've said the heat that is released by the metal is absorbed by the water, we're going to state that Q's of water is equal to minus Q's of metal. So the minus here indicates that the metal is losing heat. So each time when in calorimetry, when an object is losing heat, it's going to be denoted by minus. So water here is gaining heat, and that is why it is positive here. So we have stated that Q is equal to ms delta T. So we are going to substitute for the water and the metal here, and from there we can calculate the specific heat of the metal. So if we substitute the Q with ms delta T, we will see that So here the M is the mass, delta S, the S is the specific heat, and delta T is the change in temperature. So putting all of that together, we will see that M sub water, where W stands for water, the mass of water, the specific heat of water, the delta T sub water is equal to minus M sub metal, the specific heat of the metal, and the delta T for the metal. So we've just substituted what we have here by replacing this Q, which is equal to ms delta T. Now, if we put all of this together, we can be able to calculate the specific heat of this metal. So we use the algebra to calculate, to make S sub metal the subject of this formula. And if we do that, we are going to see that S sub metal is equal to minus mass of water times the specific heat of water times the change of temperature of water divided by the mass of the metal times delta T sub water. Delta T sub metal here, not delta T sub water. So here is delta T sub metal. So there is that minus sign. So that is how you can calculate the specific heat of the metal. We are going to see an example. Now, a chemist heats a 26.0 gram sample of an unknown metal to 100 degrees Celsius. Then places it in a coffee cup calorimeter containing 52.1 grams of water at an initial temperature of 20.0 degrees Celsius. After some time, both the metal and water reach an equal temperature of 24.0 degrees Celsius. What is the specific heat of the metal? Here we are given the specific heat of water to be equal to 4.184 joules per gram per degree Celsius. So how do we start solving this problem? We start by stating the formula first. So we know that Q sub water is equal to minus Q sub metal because the metal is losing heat. Because we are told that a chemist heats a 26.0 gram sample of an unknown metal to 100 degrees, then places it in a coffee cup calorimeter containing 52.1 grams of water at an initial temperature of 20 degrees Celsius. So the initial temperature of water is 20 degrees Celsius and that of the metal is 100 degrees Celsius. So you are putting that metal into water. Now, next thing is we are going to write out the heat equation involving the mass, the specific heat, and the change in temperature. So if we put out all of that and we are looking for the specific heat of the metal, we will see, as we saw in the previous slide, that the specific heat of the metal is the minus M sub water, S sub water, delta T sub water divided by the M sub metal, delta T sub metal. Now, let's collect all the data that we have and then substitute it into this equation. So the specific heat of water, as we've been given here, is 4.184 kilojoules per mole, kilojoules per gram, joules per gram per degree Celsius. And the mass of water, as we've been given, is 52.1 gram. The mass of the metal here is 26.0 grams, and the change in temperature for the metal is T final minus T initial. The T final here, after mixing all of them, they reached a temperature of 24 degrees Celsius, and the initial for the metal was 100. So that is going to be T final, which is 24.0 minus 100, and that gives us a value of minus 76.0 degrees Celsius. Now, the next thing, let's look at delta T sub water. So the final temperature is 24.0 degrees Celsius and the initial temperature is 20. So that is going to be a delta T value of 4.0 degrees Celsius. Now, after collecting all of our data here, what we are going to do next is that we are going to substitute all of the information here to look for the specific heat of the metal. So that is what we are going to do. Now, we have all the values that are given to us in this equation. So we substitute all of that and then we divide by M sub metal delta T sub metal, which we've already calculated here. And the next thing, we are going to cancel out the units and see which units are left. So the grams cancels with the grams, the degrees Celsius cancel with the degrees Celsius. Then we have the specific heat of the metal to be 0.44 joules per gram per degree Celsius. So this is how you get that information. Now let's look at another example. Here in this example, we are going to be looking at ammonium chloride. Ammonium chloride is a substance that absorbs heat, so it is used in making instant cold packs. So what happens is that the ammonium chloride solid absorbs heat and it is transformed into aqueous, so it dissolves in water, absorbing heat from the water. Now, to calculate the heat that is absorbed by the ammonium chloride, which is a solid, we are going to calculate the amount of heat that is lost by the aqueous solution. So here, aqueous solution, you have to take note because the ammonium is dissolved in water and that forms an aqueous solution. Now let's look at how we are going to simplify that. We already know that Q is equal to ms delta T, so we substitute the value. So the Q sub solid will be equal to minus m sub aqueous. Here, when you see the m sub aqueous here, it involves the mass of the ammonium chloride and the mass of the water. So that is the mass of the aqueous solution, which is everything contained there, and the specific heat of the aqueous solution. So most of the time, since we use water and it is the one that is in greatest amount, we are going to use the specific heat of water, and then delta T will be the change in temperature for the aqueous solution. Now let's look at this example. A 10.4 gram sample of ammonium chloride was combined with 100.0 grams of water in a coffee cup calorimeter, causing the water temperature to decrease by 6.20 degrees Celsius. Based on this information, how much heat energy was required to dissolve the sample of ammonium chloride? Calculate the heat of solution for ammonium chloride in kilojoules per mole. So when we calculate that heat, that is the heat of solution. Now the next part, we are being asked to calculate it in kilojoules per mole. So the first thing that we are going to do is that we are going to state the formula. The Q sub solid is equal to minus m sub aqueous S sub aqueous delta T sub aqueous, where minus m sub aqueous is the mass of the solid and the water that we have mixed. So it is a sum of the mass of the ammonium chloride and the water. Now let's put all of that information together. So the m sub aqueous is 10.4, which is the mass of ammonium chloride, plus 100 grams, which is the mass of water. That gives us 110.4 grams. Now the specific heat that we are using here is the specific heat of water, because much of it is water, which is 4.184 joules per gram per degree Celsius. Now the change in temperature, as we've told, is that the temperature decreases by 6 degrees Celsius. So it decreases, which means that the value is going to be minus 6.20 degrees Celsius. Now we have collected all the data that we needed to substitute in this equation. So we are going to substitute here and find the heat in kilojoules. Then from the heat that we've obtained in kilojoules, we are then going to use the mass of the ammonium chloride to calculate the number of moles, and then we divide that heat by the number of moles that we've obtained to obtain the heat in kilojoules per mole. So let's get the heat first. So the heat here is given by substituting in this value. So we cancel out what in the units that appears both at the bottom and the top. So the grams cancel with the grams, the degrees Celsius cancel with degrees Celsius, and we are left with joules. So that will give you a value of 2,860 joules. So to convert from joules to kilojoules, you divide by 1,000. That is going to give you 2.86 kilojoules. Now you've calculated the heat of solution for this ammonium chloride in kilojoules. Now, they want the heat in kilojoules per mole. So how are we going to calculate the heat in kilojoules per mole? The first thing is that we are going to calculate the number of moles of ammonium chloride for that found in 10.4 grams. So what do we use? We are going to use the molar mass as the conversion factor to convert from grams to moles, as we have already seen in the last chapters. So we have 10.4 grams of ammonium chloride. So the conversion factor here is going to be the molar mass. So we will have grams at the bottom and moles at the top, so that grams will cancel with the grams, and we are left with the moles. So from the moles now, we calculate to see how many moles we get. Now we've seen that 10.4 grams of ammonium chloride gives us 0.194 moles of ammonium chloride. Now to calculate the heat of solution for ammonium chloride in kilojoules per mole, we are going to divide the heat, which is 2.84 kilojoules, by the number of moles that we have, which is 0.194 moles. So that gives us 2.86 divided by 0.194 moles, and the answer is 14.7 kilojoules per mole. Alright, now let's look at the bomb calorimetry. For bomb calorimetry, as I've already told you, is not a bomb. In the bomb calorimetry, the bomb calorimeter contains a cage here where the sample to be analyzed is introduced. So the sample is introduced here under ignition wires. So when the ignition wires are ignited, the heat that is released here is just released into the water that you have here surrounding this system. Now there is no expansion here, so there is no work, so everything is in the form of heat. So what happens is that when that ignition occurs, there is that bomb, like you see the boom, everything, the heat is now transferred into the solution, which is the water, and we can calculate everything that we need. Remember, we've said everything here in the bomb calorimeter, we are using Q is equal to C delta T, because we are using the heat capacity. Now the bomb calorimeter measures the energy content that is involved in food and fuels. So Q is equal to C delta T. So each apparatus that we use, we have the specific heat of that apparatus that the heat capacity, we have the heat capacity, and then we are going to measure the change in temperature in the water. So that is going to give us the value for the heat. Now let's look at an example here. A chemist places a 20.0 gram sample of ethanol inside a bomb calorimeter with a known heat capacity of 28.72 kilojoules per degree Celsius. When the ethanol ignites, the temperature of the calorimeter rises from 22.04 degrees Celsius to 42.74 degrees Celsius. How much heat did ethanol release? Calculate the energy released in kilojoules per gram of ethanol. Now, it's important to note what you're asked. Kilojoules per gram. The other one we did was kilojoules per mole. Now we are calculating in kilojoules per gram. So the first thing, we are going to calculate the heat in kilojoules, and from there we are going to divide the heat by the grams of ethanol that has been given to us to have the heat in kilojoules per gram. Now, how do we calculate the heat? As we've already seen the formula, it is given by Q is equal to C delta T, and here for delta T is 42.74 degrees Celsius minus 22.04 degrees Celsius. That gives you 20.70 degrees Celsius. Now, we've been told that the heat capacity of the bomb calorimeter is 28.72 kilojoules per degree Celsius. So we know that Q is equal to C delta T. We are going to substitute the values right in here and cancel out the units that appear at the top and at the bottom, which is the degree Celsius. So we see that the answer that we obtain here is in kilojoules. So if you do that calculation, the answer is 594.5 kilojoules. Now the question asks us to calculate the energy released in kilojoules per gram of ethanol. So what we are going to do now, we are going to divide the heat here by the number of grams given to us in the question. So it's going to be 594.5 kilojoules divided by 20.0 grams, and that gives us a value of 29.7 kilojoules per gram of ethanol. Now let's look at the last part of this lecture, which is heat energy and chemical reactions. So chemical reactions involve changes in energy, and energy of a reaction is an extensive property. When we talk of an extensive property, we mean the property depends on the mass that is present. So as opposed to intensive property, which does not depend on the amount of substance, extensive properties depend on the amount of substance. So the heat energy of a chemical reaction depends on the amount of mass that is present. So an example here is that the amount of heat that is released by this fire in this small campfire is small compared to the amount of heat that is released by this burning forest, because we have so much mass here in the forest as compared to this little campfire. Now let's look at what is called fuel value. Fuel value is defined as the amount of energy that can be produced by combustion of a material. Just like we saw for ethanol, the fuel value for different materials like ethanol, methanol, and other substances, they vary. And a higher fuel value means that the substance will release a higher energy. So looking at the table here, these are the fuel values for common combustion fuels. So we see methane here with a fuel value of 55.5 kilojoules per gram, natural gas with a fuel value of 54.0, propane with 50.3. So we are using a gram. So if you use 1 gram of methane, it produces 55.5 kilojoules. If you use 1 gram of natural gas, it produces 54.0 kilojoules. So this, amongst all of these, methane will produce the highest amount of heat or energy here. Now let's look at the reaction enthalpy. Reaction enthalpy is called delta H reaction, and the reaction enthalpy can be defined as the amount of heat energy that is absorbed or released in a chemical reaction at constant pressure. So it's very important here, constant pressure. Now looking at this equation here, we see that this is the combustion of ethanol to give us carbon dioxide and water, and the sign of delta H reaction here shows that it is negative. And we already looked at exothermic and endothermic reactions. For exothermic reactions, delta H value is negative. It means that heat is released. And for an endothermic reaction, delta H is positive, which means that it is absorbing heat. So we can use this equation to show the conversion factors from this equation, the balanced equation. We see that if we have to show the conversion factor for the ethanol, we will see that minus 1368 kilojoules, we used 1 mole of ethanol. If we have to use that for oxygen, we'll have minus 1368 kilojoules for 3 moles of oxygen. So we can use that for reactants and products. So for the products, which are carbon dioxide and water, the same amount of kilojoules for carbon dioxide will be 2 moles, and for water it will be 3 moles. So that is a conversion factor. Now let's look at an example here. How much heat will be released by the combustion of 789.0 grams of ethanol? We've been given the balanced equation, and then we have been given the delta H reaction. So how much heat will be released by the combustion of 789. We know that if we combust 1 mole of ethanol, it gives minus 1368. Now, what we are going to do is that we are going to use this mass, convert it to moles, then use the conversion factor. Here, 1 mole of ethanol gives minus 1368 kilojoules. So let's start by converting the grams to moles. Then from the moles, we use the mole fraction here, the conversion factor, to get to the energy. So let's start with the grams and convert it to moles. So we are going to move from grams to moles using the molar mass. So the molar mass of ethanol is 46.08 grams per mole. So the grams will cancel with the grams, and we have the moles of ethanol. Now with the moles, we are going to use the conversion factor in this balanced equation, where we've seen that 1 mole of ethanol will give minus 1368 kilojoules. So now we are going to cancel out the moles of ethanol, and we are left with kilojoules. So that is, if you carry out that calculation, you will see that it gives us minus 2348 times 10 to the 4 kilojoules. The minus just shows you that it is an exothermic reaction. So the amount of heat that it actually gives out is 2.342 times 10 to the 4 kilojoules. So that is how you do the calculation. Now let's look at this other calculation. Many manufacturers produce hydrogen gas from methane gas as shown in the reaction below. This reaction is endothermic with a delta H reaction of 206.1 kilojoules. How much heat energy is required to produce 1.00 kilograms of hydrogen gas? Now, if you look at this reaction, the balanced equation here, you see that 3 moles of hydrogen gas gives 206.1 kilojoules. So now we are going to use 1 kilogram of hydrogen gas and see how much of the heat that gives. So the first thing that we are going to do here is that we are going to convert the kilograms to grams of hydrogen. Then from grams of hydrogen, we are going to convert it to moles of hydrogen. Then after getting the moles of hydrogen, we are now going to use the conversion factor here. 3 moles of hydrogen gives 206.1 kilojoules. And then we get the value. So let's start by first converting the kilograms to the grams, and then to moles, and then finally to the energy. So let's see how we convert kilograms to grams. So if we want to convert from kilograms to grams, what do? We know that 1 kilogram is equal to 1000 grams. So in this conversion, kilograms will be found at the bottom, so that it cancels out with the kilogram from the 1.00. Now that is the conversion factor, and here the kilograms cancels out, and we are left with grams of hydrogen. Now we have to convert from grams of hydrogen to moles of hydrogen. What you have to take note here is hydrogen is a diatomic molecule. So if you look at the periodic table, you will see the mass of 1 atom of hydrogen. So here is 2. So take note of that. So you have to multiply that by 2, and that will give you 2.02 grams of hydrogen. So we see here that the grams will cancel with the grams of hydrogen, and we are left with moles of hydrogen. Now we are going to use the conversion factor here in this balanced equation, that 3 moles of hydrogen gas, they give 206.1 kilojoules. So that is what we will multiply with. So we see the 3 moles of hydrogen at the bottom. The moles of hydrogen cancels with moles of hydrogen, and we are left with just kilojoules, and that gives us a value of 3.40 times 10 to the 4 kilojoules of energy that is required of hydrogen gas. Alright, now let's look at the physical changes that are involved with enthalpy changes. Now, for example, when we are melting ice, it needs to absorb heat energy for it to melt. And for freezing, if you want to freeze ice, it has to release energy. so it is an exothermic. For the melting, it's an endothermic, it has to absorb, and for freezing, it's an exothermic process. So same thing here. Now for the summary, we have seen the reaction energy is an extensive property. We have seen that the fuel value is the energy that is released in the combustion reaction, and we've seen that the reaction enthalpy relates heat released in a reaction to a balanced equation.